Alright y'all, so here's some help for you when you get to worksheet 5. Again, on worksheet 5 we're really just introducing a different style of factoring which we can use our area model on, which makes it nice, and then we're going to graph. Now the biggest thing here is before we start using the area model, always every single time start by looking at all four of these terms here and ask yourself, is there a greatest common factor? Because if there is, we can factor that out and it'll make our lives a whole heck of a lot easier. X cubed, 4x squared, negative 4x, and negative 16, those don't have any numbers in common, right? This one doesn't have 4. They don't all have x's, so there is no greatest common factor, but you need to start there first. After that, to factor this, we can just set up our area model, right? So we set up our area model. And this is like how we factor trinomials, but they've already done all the work, right? We have these four terms. We're just going to place them in the area model. I'm just going to go from left to right, right? So the x cubed in the upper left-hand corner, the positive 4x squared in the next box. Now go down to the bottom left box, negative 4x, and then that last box we can fill in with the negative 16. From there, again, we don't have to do much, we just have to find the greatest common factor of each row and of each column, right? So it's just that last step there. X cubed and negative 4x, they just have an x in common. Excuse me. 4x squared and negative 16, well, you can divide both of those by a 4. We can't do anything with the x's, so it's just a 4, and specifically because that's a positive 4x right there, that's going to be a positive 4. So we get a factor of x plus 4. Okay, now let's look at the rows. So that first row, x cubed and 4x squared, well, they both have x squared, so we can take an x squared out of both of them as a greatest common factor. And for that last one, negative 4x and negative 16, we can divide both of those by a 4. Specifically, it's going to be a negative 4 because that's a negative 4x right there. So what we just found was this this expression here factors down into x plus 4 and then x squared minus 4. But we're not done. We can actually go further. Hopefully you look at this x squared minus 4 and you notice that is a difference of squares, right? We know what the square root of 4 is. Again, that's this process here where I would set up these parentheses and say x to the second power is x squared, 2 to the second power is 4, which lets us break that further down into x plus 2, x minus 2. So you have to make sure you factor completely here. The x plus 4 is still out in front. That is fully factored, and now we can go through our steps of graphing. I'm going to take this and put it over on the side, and we can finish this up. X plus 2, x minus 2. Okay, first step, what's the end behaviors? Right, now again, when we have this standard form over here, right, where there's no parentheses, it's really quick to find the degree and leading coefficient. The degree is 3, that's the highest exponent. The leading coefficient is, there's no number in front of x, so it's just a 1. Now, if you didn't want to do it that one, you took it from this factored form here, you would do this x times this x times this x, giving us the x cubed, right, because x times x times x is x cubed. We're looking at the same thing here from that standard form, where your degree is 3, your leading coefficient is 1. From here on out, when we're doing these problems, I'm going to only look at the standard form just because it's a little bit easier, but notice you can do it in either way. But what that tells us is leading coefficient's 1, that's positive, the right side goes up. Degree is odd, that means that your end behaviors go in opposite directions, the left side then has to go down. So our end behaviors are taken care of. Now we move on to our x-intercepts. Again, to find x-intercept, you just set each of these factors here equal to 0. So x plus 4, x plus 2, x minus 2. Okay, so we should get x equals negative 4, x equals negative 2, x equals positive 2 by solving those. Those are our x-intercepts. The last thing that we care about for x-intercepts is, do we pass through those x-intercepts or do we bounce off the x-intercept? And again, what you look at is the multiplicity. All of these have an exponent of 1. They're all represented once. That's all multiplicity of 1, telling us that each of those x-intercepts, we're going to pass through that x-intercept. Okay, so our x-intercepts are taken care of. I'm going to put those on our graph now. We have one at -4, and we're passing through. We have one at -2, and we're passing through. And we have our last x-intercept here at +2, that's passing through. There's one last step here, and it's finding the y-intercept. To find the y-intercept, again, we just set x equal to 0, and we can solve. So we can take x and plug it in for 0 here, and we're going to go y equals 0 plus 4, 0 plus 2, 0 minus 2. That's 4 times 2 times -2. 4 times 2 is 8. 8 times -2 is -16. So we get this y-intercept of 0, -16. Once you get that, you can put it on your graph. Now, before we finish this off and actually graph it, notice how anytime they give us our equation in standard form, do you notice something about the y-intercept? We just got 0, -16. Look at this last term here that doesn't have a value of x. It's -16. It's because when we have this equation in standard form, it's really nice and easy to find that y-intercept, because if we're just replacing zeros or x with 0, everything here, 0 to the power is 0. 4 times 0 to the second power is 0. Like 4 times 0 is 0, leaving us with that -16. So it's a little bit quicker than when it's in factored form. But again, it doesn't matter which way you find it. If you feel more comfortable doing it like this, then do it like that, right? This is just a quick way of noticing, oh, y-intercept's -16. But with all of that, we can finish off our graph here, right? Use the m behaviors. Left side goes down. Okay, so it goes down. We get to this x-intercept here at -4. We're passing through that x-intercept, so we go into those top 2 quadrants. Come back to that next intercept at -2. Again, we're passing through. You go down into those bottom 2 quadrants. You hit this y-intercept there at -16. Make sure you come back to the last x-intercept there at +2. And we end by going up, which is good because the right end behavior goes up. That finishes off our graph. Now again, what we added in was this idea of factoring by grouping, or factoring these 4 terms, which we can just use our area model. Other than that, all of the steps for graphing are the same. Again, I took my time on this problem, showing you everything that goes into it. But as I go through these next couple of examples, I'm going to go a little bit quicker there. All right, also here's number 18. Again, we're going to go through this a bit quicker, because all we're really adding in is the factoring by grouping bit. The first thing that we do, again, every single time you're doing this and every single time we factor, is start out with the greatest common factor. That means when you look at these 4 terms here, do they have anything in common? And in this case, 3, 9, 27, and 81 can all be divided by a 3. So we're going to do that first. Okay, so we're going to factor out the greatest common factor of 3. That 3 sits out in front, and again, what we're doing is we're taking a 3 out of each of these terms. So we take the 3 out of 3x cubed, we're left with just an x cubed. Do the same with the 9x squared, we're left with the 3 and the x squared. With the 27, we're doing -27 divided by 3 is 9. We're still left with the x. And that 81, we can divide it by 3. -81 divided by 3 is -27. So you have to start with the greatest common factor there. Now we end up with these 4 terms, and this is where we can use that area model to work this out pretty quick. Again, just place those 4 terms in the area model from left to right. You're going to put them in the box from left to right. So x cubed in the upper left hand, positive 3x squared in the upper right hand. I'll move down to the bottom, negative 9x and negative 27. To finish off the area model, you're doing the greatest common factor of each column and in each row. X cubed and 9x have an x in common. 3x squared and negative 27 have a positive 3 in common. Again, if you need some help with the area model, make sure you let me know so I can work with you a little bit more. I'm going to go through this faster because we've done it a few times here. X cubed and 3x squared, we're looking at this first row now, have an x squared in common. And then negative 9x and negative 27, we can divide both of those terms by 9. Specifically, it's negative 9 because that's a negative 9x. Oh, and that gives us our factors of the 3 still in the front. We get x plus 3 and x squared minus 9. But we're actually not done because x squared minus 9, this is a difference of squares. We can factor that further. Again, because we know x to the second power is x squared and 3 to the second power is 9, allowing us to write that as 3 times x plus 3 from this. And then this x squared minus 9 breaks down into x plus 3, x minus 3. There's a lot of 3's here, but there's one last step that we can do here, and it's we can combine these x plus 3's. We can represent those as x plus 3 to the second power. Everything else will follow along. And that is our completely factored form, which I'll take off over here to the side. Okay. Now here we go. Let's start with our graphing, right? Graphing, we need the M behaviors. Again, for the M behaviors, we need that leading coefficient, the degree and leading coefficient. Again, we have it in standard form over here, right here at this step. So I'm just going to look at that and say that the degree is 3, that leading coefficient is 3. Because the leading coefficient is positive, the right side goes up. Because the degree is odd, the left side goes in the opposite direction, it goes down. The second thing we look at are the x-intercepts. Again, to find the x-intercepts, we set each of those factors equal to 0. So we're going to go 3 equals 0, x plus 3 equals 0, x minus 3 equals 0. 3 equals 0, x plus 3 equals 0, x minus 3 equals 0. This 3 equals 0 right here is not going to tell you anything for x-intercepts because it doesn't have an x. X plus 3 is an x-intercept at negative 3, x minus 3 is an x-intercept at positive 3. Right, we're thinking opposites there. The last thing is determining do we bounce or pass through at those x-intercepts. For x plus 3, notice how it has that exponent of 2. Remember, exponents of 2, which is a multiplicity of 2, tells us that we're going to bounce at that x-intercept, where this x minus 3, it's only represented once. That's a multiplicity of 1. We're going to pass through there. And with that, we can add our x-intercepts on the graph, right? There's one at negative 3, there's one at positive 3. That x-intercept at negative 3, we bounce. That x-intercept at positive 3, we pass through. Now, the last thing that we have to do, right, we went through, we found our end behaviors, we found our x-intercepts. The last thing you have to do is find the y-intercept. Now, again, the fastest way you can do that is we're setting x equal to 0. Notice what happens if you do that over here at our original equation. You plug in a 0 everywhere for x. All of these terms zero out, leaving us with negative 81, telling us that our y-intercept is 0, negative 81, right? It's really nice when it's in that form. Or you can go to this factored form right here, plug in 0 for x, solve that, and I'm telling you, you'll still end up getting negative 81 no matter what. We have a y-intercept down there at 0, negative 81, so just make sure you label it. And we can finish off this graph here. Again, start with the M behaviors. The left side goes down. So if that farthest left point, we could go down. We get to that x-intercept there at -3, we bounce off that x-intercept, so since it's down, we're going to go right back down, which is good because now we can hit that y-intercept at 0, -81, come back to that last x-intercept there at 3, and pass through it into those upper two quadrants. Finishing off our graph, again, checking off that that right indicator goes up. So the biggest thing here again on these examples is we have to do a little bit of factoring there. Hopefully the time that we spent on unit 2, where we spent a lot of time looking at difference of squares and factoring trinomials and everything like that, is really able to benefit you as you go through these problems. Alright y'all, so here's number 20. It's the last one that I'm going to do here for worksheet 5. Again, if you need any extra help or you have questions, please send me an email from my office hours so we can figure this out. But the difference here on number 20 is we just have to set this up first, which is telling us to set up f of x minus g of x. And the biggest thing is you have to be careful there, right? When we set this up, f of x is 4x to the 4th plus 8x cubed, and we're subtracting g of x. So we're subtracting the 16x squared plus 32x. The biggest, or the most important part about that is we're subtracting both the 16x squared and 32x. So I like to put those parentheses around there to remind me that that minus is to the 16x squared and to the 32x, telling us that really what we're doing here is 4x to the 4th power plus 8x cubed minus 16x squared minus 32x, because we're subtracting both of those. That's our function. Now we're at this step, just like we were on those previous two examples, where we can factor this, right? Start with the greatest common factor. You look at all 4 of these terms. First thing I noticed is all of them have an x, so we can factor out an x. Second thing I noticed is 4, 8, 16, and 32. All of those can be divided evenly by a 4. So it has a greatest common factor of 4x. That 4x sits out in front, and what's left in the parentheses is what we have left over after we factor out that greatest common factor of 4x. So we take 4x out of 4x to the 4th, we're left with x cubed. We take 4x out of 8x cubed, we're left with 2 and an x squared. Again, by dividing, that's how we're getting this. That 16x squared, we're left with a 4 and an x. And that negative 32x, negative 32 divided by 4 is negative 8. We took the x out, so that's all we're left with. Now to finish this problem off, we do need to factor what's left in the parentheses here. And that's when we set up our area model. So set up your area model, and what we're going to do is we're going to fill in the area model with what we have here. So the x cubed, upper left, positive 2x squared. I'm just filling it in one at a time. Negative 4x here and negative 8 at the end. Again, this is the 3rd time we're going through this, so I'm going to work a little bit quicker. You're doing the greatest common factor of the columns and of the rows. X cubed and 4x have an x in common. For that second column, 2x squared and negative 8 have a 2 in common, and it's a positive 2 because that's a positive 2x squared. Now we're looking at the rows, so I'm looking at the top row. X cubed and 2x squared have an x squared in common. Negative 4x and negative 8, well 4 and 8, you can divide both of those by 4, and specifically it's going to be a negative 4 because that's a negative 4x, which allows us to write this as, we still have the 4x out in front, x plus 2, and then x squared minus 4. Now we're not done, but I'm going to take this over to this side so I have a little bit more room to work with. Why we're not done is because that x squared minus 4 right there, that's a difference of squares, right? We can factor that further. We know that x to the 2nd power is x squared, 2 to the 2nd power is 4, So that factors into x plus 2, x minus 2, using the difference of squares. Everything else is still tagged along, so there's still that x plus 2 from the beginning, and the 4x that we factored out at the very beginning. And the last thing we can do here is combine these x plus 2's as an x plus 2 squared, leaving that x minus 2 at the end. That's factored completely. Now, again, the reason why we factor these completely is so we can find where the x-intercepts, right? That's the biggest part there. But now we're going to go through our graphing process, right? Start with the end behaviors, right? End behavior, it's nice because we have this form right here, which is our standard form. Look at that. The degree is 4, the leading coefficient is 4. Because the leading coefficient is 4, which is positive, the right side goes up. Because the degree is even, the left side goes in the same direction, it also goes up. Okay, the second part, what are the x-intercepts? Yeah, find the x-intercepts. You set each of the independent factors here equal to, so we're going to say 4x equals 0, x plus 2 equals 0, x minus 2 equals 0. This gives us an x-intercept at positive 2. This is at negative 2, and this last one. Divide by 4 here. You get an x-intercept at 0. So we have 3 different x-intercepts. The last thing about x-intercepts is what's the multiplicity, because that determines do we pass through at that point or do we bounce off the x-intercept. For this x-intercept for 4x, notice how that's 4x is just to the first part, there's only one representation for that, so that's a multiplicity of 1, odd multiplicity you pass through. Versus, look at this x plus 2, right? X plus 2 in our factor form there has that exponent of 2, telling us that it's represented twice, right? We had it represented twice here when we factored it. That's a multiplicity of 2. Even multiplicities, we bounce. So at negative 2, we're bouncing. And that last one for that x minus 2, again, it's only represented once there. Multiplicity of 1, we're going to pass through. With that, we can add our x-intercepts onto the graph. So there's one at 0, and it passes through. There's an x-intercept at negative 2, and it bounces. And there's one at positive 2. That passes through. To finish off this problem, we need to find the y-intercept. And this is going to end up working out real nice for us because anytime we have that x-intercept there at 0, anytime you have that, your y-intercept is automatically 0, 0, no matter what. Because the x-intercept and y-intercept end up being at the same place. So we can just go down here and make sure you label it 0, 0. We have all of our information, the end behaviors, x-intercepts, y-intercepts. To finish it off, we just need to do a little graph here. So use the end behaviors. The left side goes up. So that left end behavior, that farthest left point, we just need to make sure it goes up. You get to that x-intercept there at negative 2, and we're asked to bounce. So we get to that x-intercept and we bounce right back up into those top 2 quadrants. That's the bounce. You can go up however far you want. Just make sure you come back to that x-intercept there at 0. We pass through that x-intercept, so we're going from the top 2 quadrants down into the bottom 2 quadrants. Come back to that last x-intercept there at 2. Again, we're passing through that x-intercept. So we're going to go from the bottom 2 quadrants to the top 2 quadrants, ending up with the graph that looks something like that, which is good because the right side ends by going up there. That finishes off number 20 for you. Again, on some of these problems, it's really just adding in some steps where you set up function notation, and then after that, make sure you're being careful. Always start with the greatest common factor, and then when we have these 4 terms, factor it using the area model. Factor it completely, so you have to make sure you break down our difference of squares when that pops up, or if it was a trinomial, you need to make sure you factor that completely as well. And then you're into your steps of graphing. I understand that these take a little bit of effort. That's why I'm just assigning you those 4, and it's good practice for you. for factoring and for your graphing. If you have any more questions, feel free to send me an email, reach out to me, or come to my office hours.